Hi everybody, this is just going to be a little demonstration here about how to graph your electron energy versus light frequency graphs. So as you guys have probably seen now, here right now I have sodium. You guys are going to choose between zinc, copper, platinum, or calcium metals. That's the metal that you have here. But you can see that you can increase the intensity, and you see the electrons shooting out right here, and I can detect a current there as well. So that's telling me that there are electrons being shot out of the plate. That's what the current is telling me. But you can see this battery here is saying 0 volts. Now if I turn the battery to the right, that actually just increases the current, the speed at which the current moves, because essentially the battery is creating an electric field through here, and it's making that the electrons will travel faster through. So your goal here is not to make them move faster. It's to get the electrons to stop right at this side right here on the right side of the plate here. So how much of the battery needs to push in order to get the electrons to, okay, looks like, okay, if I do 0.4, that's a little less current. Oh, right there. Right about there. I could go back a little bit. So at about 0.8 it looks like. So it's negative just because it's pointing in the opposite direction. I'm not going to worry about the negative. But at about there I'm getting 0 current. So 0.8 volts for my battery is when my electrons are stopping just at the edge, right? If I did 0.6 I still got a current, but then 0.8 is about where it starts. We call this a cutoff voltage. But yeah, so it starts to cut off right there. So what this is basically showing, so here is my electron. So let's say here's my electron, right? At first it's getting shot out with some kinetic energy, but then when it reaches here, well, then it all of a sudden is at rest, right? So essentially we say that the kinetic energy is equal to 0, but it does have now, it's got electric potential energy. So the electric potential energy is whatever the kinetic energy was when it got shot out. Let's say that was equal to, I don't want to give numbers actually. So the kinetic energy at which it shot out is equal to potential energy now that it gained from being here, because then it's going to fall back down. This is the same idea of, if I get a ball, right, and I get that ball and I throw the ball up in the air, it's going to reach a point where it stops and then comes back down. This is where it has its maximum potential energy. But it has that potential energy because I threw it up in the air, and that's what gave it kinetic energy. So again, the light is kicking the electrons out. That's what gives it the kinetic energy. But then once it reaches here, if I have my battery situated, remember this is now at 0.8 volts, and my current is now 0. Well, it's really negative 0.8 volts, but again, I'm ignoring the negative. I don't care about that for my graph. The kinetic energy will stop, and it'll have some potential energy. What is that potential energy? Well, it ends up equaling what we call 0.8 EV. EV, this is electron volts. And it's a measurement of energy. It's like saying joules. It's just a different way to mention it. And what it is the amount of volts it takes to stop an electron. That's literally what it means. It's the amount of voltage it takes to stop an electron. How much voltage did it take to stop the electron? 0.8, hence why it has 0.8 eV. Basically, when energies get really small, we stop using the term joules and we just start using EV instead, because it kind of clears the palette, if you will. It makes things a little easier to I want to say digest. Instead of saying, like something times 10 to the negative 19 joules, I can just say something electron volts, and that makes things a little easier. So when we got these small energies, we use electron volts. But the thing is that you want to be able to use, so I had 0.8, so I had 0.8 electron volts, and the wavelength was 400 nanometers. So at 400 nanometers, this is one data point, I got 0.8 EV. So what I would do then in your graphs that you guys have, so again, the graph is called photoelectric plot. You click on this and you'll get a graph like this. At 400 nanometers, that's what you'll write down here. So, by the way, you're going to have well, here, this one just turned into platinum. You would write down your metal right here. This is where you write down your metal, and then just delete this. Just highlight it and delete it, and then that'll be the metal that you're going to use, which is right here. So I would change to platinum. But I'm going to use sodium just for this example. So I have 400 nanometers, and then the energy was 0.8 eV. That's how much energy the electrons had leaving right there. So a couple things I want to convert to wavelength, and then I convert to frequency. So converting from wavelength to frequency, I'm going to say, we've done problems with this already where the wavelength of something and the frequency of something. You should be able to calculate that, knowing that the speed of light, right? The speed of light is equal to 3 times 10 to the 8 meters per second. But then to convert to nanometers, well, there is 1 times 10 to the 9 nanometers in 1 meter. So if I know that, then if I wanted to convert from 400 nanometers to meters, I would do 1 times 10 to the 9 on the bottom here, nanometers, and then 1 meter up top. And that'll give me my meters. Nanometers will cancel nanometers. So I'm doing 400 divided by 1 times 10 to the 9, or times 10 to the 9. So if I do that, I can do that here by saying, okay, equals 400, whatever 400 was, that was A2, divided by 10 to the power of 9, right? 1 times 10 to the power of 9. So there we go. That's going to do my conversion for me. And I hit enter, and boom, it just gave me the wavelength in meters. And once you got all your wavelengths in here, remember, you can let's say I get 500, 600, 700, etc., and I want to do that calculation over and over. I just click here, click to the bottom corner, and I drag all the way down, and it just does that calculation over and over and over. It did the same calculation over and over and over, and I can do that all the way down to my bottom wavelength, and I can even do that with frequency to calculate the frequency. And then again, I'm going to use energy. I'm going to get the energy that the electron has as well over here. And to get those other energies, so if I change the frequency, that's what you're changing, or the wavelength. So I go to a shorter wavelength. This is 304 nanometers. You see now I got a current here. So I need to make the battery move a little more. Somewhere around there. I'll say around -2 volts. So I'll say at 304 nanometers, it's -2 volts. So it's another thing now I can plug in there. At, well, none of this is really true. So at 304 nanometers, I got -2 volts, so that'll be about 2 right there, electron volts. And then I can convert this because I can just drag this down, and that converts then that for me to 304. And I can keep doing this until I get up to 10 data points. Once you're done with all that, you're going to graph frequency versus energy. That's the energy of the electrons versus the frequency of light in hertz. So the energy of the electrons in eV, frequency of light is in hertz. So you're going to graph that, label it, title, trend line, equation, R squared value, all that good stuff. And then that's what you're submitting to me at the end. So yeah, I hope that helps. I hope that that helps you see how to graph things. All right, bye.